Aniket, Dhananjay, and Ilakya present to you our project Security for Multi-Tenant FPGA. An FPGA is an excellent resource to host several circuits as well as users on a single board. However, when several users are hosted on a single FPGA board, we might run into certain security issues. Let's see what they are. Only the programmable logic is isolated, whereas the power delivery network is common in an FPGA. Therefore, the several users will share a common power delivery network, and thus malicious circuits can take advantage of this and wreak havoc on the other circuits. For example, let us consider Iron Man and Hulk to be the normal circuits, whereas Thanos is the malicious circuit. When the FPGA is in the hands of Thanos, then it can go boom. In order to understand the activity of different circuits on the FPGA board, Professor Kastner's research group has built a voltage sensor which contains carry chain adders. Changes in the delay of this adder can give useful information about the power consumption of the various circuits. In the beginning of the quarter, we set out to build a present cryptographic HLS core, implement it on the pink C2 board, and integrate it with the PL sensor. We also set out to collect traces from the already existing course built by Professor Kastner's research group and give it to a CNN classifier in order to understand the activity on the FPGA. We have built the present cryptographic HLS core and implemented it on the pink Z2 board. We have also integrated it with the PL sensor and are in the process of collecting the traces.
Before we analyze any signal, we need to know the nature of the signal that we have. Now, the nature of the signal that we have is non-stationary and is of varying length. A non-stationary signal means that different applications are happening at different time instances. Of varying length means that these different algorithms have different runtimes. Now, this means that the frequency response changes for the data as the time frame of observation changes. Thus, a global transform analysis method like Fourier analysis would not work in our situation. So when we had to select a classifier input, we settled on the spectrograms because they were easier to compute and also gave us a good representation of what frequency components existed at a given instance of time. Now, the spectrogram was computed over 8197 samples, which corresponds to the smallest duration for which an algorithm runs for. Within each spectrogram, the window time interval was selected to be 256 and the overlap was decided to be 32 based upon various heuristics. For each application, we used about 150 training traces, 50 validation traces, and 50 test traces. Over here, we can see the matrix to be a visual representation of the accuracy with which each core is being classified. We see very high accuracies for almost all the cores. One core that is present MVA shows a lower accuracy of classification as compared to the others. This is because it is being misclassified as AES-MB. One possible reason for this is because when the samples were actually being collected or the traces were being collected even after the execution of the present MB application had finished or had completed. This means that the traces collected were collected for a time duration when present MB did not even run. So a possible solution to increase the accuracy of the classifier is giving better data collected from the traces. So in conclusion, we have achieved the milestones that we set out to achieve. However, there is a lot more work that can be done in order to improve the accuracy of the classifier and the number of cores it can classify. And we also wish to thank Professor Kastner for giving us this opportunity to work on this incredible project. Thank you.